which
Okay, so our next speaker is Martin Albrecht from Royal Holloway
University
from England, and he's going to talk about commutative algebra in Sage, a status report.
Okay, specifically, I'm going to give you an introduction, and then I'm going to present, the implementations we have, give you some details, and the most interesting part is probably, so what can we do by now? And the fourth part is totally not related. It's about sparse linear algebra over FP, which is, you could say it's somehow related, but basically I just wanted to use the time and talk about this for.
Awesome.
I announced it on the mailing list, so it's not bad here. Okay, anyway. So what's going to be covered here? Commutative algebra means a lot. A lot of this stuff is covered elsewhere. I'm only going to be talking about multivariate polynomial rings over fields and commutative rings. Okay. So before I start, I just want to give you this is the slide which was my to-do list exactly 1 year ago in October 2006. This is what I said. We need to do that. And by then we weren't even dreaming of the speed we have now for multivariate polynomial arithmetic. Some stupid ideas like porting our e-tuples. I'll explain to you what these are from Pyx to C to keep up with singular, because I actually benchmarked singular using the interpreter, which is really slow. So we get totally false impression on how fast singular actually is. It's so much faster. So basically the first point, it's all ridiculous, and we are streets ahead. Also, I've used my last talk as well, so I was talking about sparse linear algebra as well. And actually, this isn't done yet. But there's some new hopes. Also, I'm going to talk a little bit about Polyboring, which is supposed to fix also a yield problem about efficient implementation of the quotient ring over F2. Cryptographers are very interested in. And the stuff at the bottom is pretty much here, right? You could just ignore it.
What's field ideal mean?
The field ideal is in this case, it's x to the power 2 plus x, and this for every variable. And
so it's one specific ideal.
Yes, okay. Yes. And actually, in Sage, if you type sage.rings.ideal.field ideal bracket and your polynomial ring, you get an ideal that's exactly this.
So when you say streets ahead, is this a pun meaning that you're using Strauss's algorithm, or?
No pun intended.
Okay.
We are just multivariate polynomial arithmetic over finite fields is really good. Okay, but I get to this. So basically 1 year ago I was dreaming about F5, and this would involve serious work.
But you're not going to do that.
Yeah, and none of that involves serious work.
Okay, so what do we have? Right, so this is the inheritance tree, and part of it is not yet implemented. So basically, you start off with a commutative ring.
Mark, I'm sorry, can I have to make that slide? Did you do this manually?
Yes, manually.
I'm sorry.
We need to.
I wouldn't keep it secret from you, Chris.
It's an open source slide.
No, I just manually types it. In any case, so you have your commutative ring, and over this ring we basically have, for the purpose of this talk, we have an M polynomial ring generic, which is just common operations, which usually don't need to be fast, very generic, as the name implies. And from this guy we inherit something which is our generic implementation, which is the M polynomial ring polydict. I'm going to go into the details of these implementations in a sec. And then we have this kind of new M polynomial ring live singular, which uses singular for the multivariate polynomials. And here's the first thing that's supposed to pop out, but I'll get to that in a second. And then the red stuff is not implemented yet. So, and eventually we'll also have M polynomial ring cocoa, which links against the cocoa lib Michael is going to be talking about. And you basically have a similar inheritance tree for the quotient ring generic, So you have your common operations, and then you get your polynomial quotient ring, which is supposed to be the generic implementation, and the Boolean polynomial ring is implements.
Oh, that's what the name is.
Yeah, Polyboring.
Yes. So it's and for this, so this fits kind of nicely in the inheritance tree. As you can see, this inheritance tree has a flaw because quotient ring underscore lib singular doesn't inherit from quotient ring generic. The reason is that it's much more convenient to just inherit this way because it's basically the same as these things, right? I mean, the multiplication is different, but besides this, it's basically the same. So if I was to move this guy down here, I would have to re-implement everything here, or add another function call and make a lot of functions that implement the functionality. So
actually, regarding that, is it the does that from users' perspective, will that make life any different for them? Like, do you usually just start working with commutative ring? Is that
sure.
right?
There's one thing, we have all these funny is underscore and some element type functions.
Yep.
And you're supposed to call these instead of calling is instance. Right? If you're a Python programmer, you're kind of used to just call is instance and my object and then a type. And this will fail. I mean, if you ask an element from this ring, if it's of a type, if it's quotient ring is instance, it will fail.
Nice.
But if you call is underscore quotient ring, it will return true. So. Yeah, basically for ideals we have the generic ideal, and then you have an n-polynomial ideal, which is all the multivariate polynomial rings, and then you got a Boolean polynomial ideal, which is gives you access to the Polyboring stuff. Why is it? It's not supposed to be generic, but polydict. Okay, sorry. So this is the standard implementation that's been in Sage for ages, and this was the implementation I was dreaming of making faster last year. And it's very generic, so it works over any base ring, but it's really slow. And obviously, works means you can add polynomials and multiply them. You can compute Grübner basis or something like this. So for instance, right now we are providing the integers as a base ring are implemented this way. And how is it implemented? It's basically a dictionary of dictionaries. So the inner dictionary contains a mapping from the index of a variable to the exponent, and then the value of this dictionary is then the coefficient. So this is how these are implemented. And
so you're using a dictionary on the inside, is that so you can handle large numbers of variables?
Yes.
More space efficient.
Yeah, and it's also a bit faster.
Oh, really?
Well, it depends. I mean, the crossover point is quite early.
So like even for 3 variables or something?
Yeah, but if the singular, for instance, they're using a C array here, and this would be faster, obviously.
Does singular handle like large numbers of variables or only small numbers?
Yeah, you can just say, give me a ring with 6,000 variables.
And is it going to store a vector of that length for each one?
As far as I know, yes.
Sort of linear in that number?
Yeah.
Or does it get uglier as it goes up?
No, it's linear. It's just a array, as far as I know. They might have some special tricks for really large numbers, but because it's really, it's written in C++ singular, but at the time they wrote it, the templating functionality wasn't really stable. So they wrote a lot of macros, and it's quite difficult to figure out which implementations actually used. So this is kind of a bit of tricky. So, but yeah, they're using an array. So one could eventually switch to an array there. I mean, there are lots of optimizations possible for this implementation, and we should consider at some point if it's worth it to improve it, because it will work over everything.
The first version of this actually had arrays. It had Python arrays, and it was David Joyner wrote it, and it was really slow. So then I rewrote it to use Python dictionaries, and it was only really slow. And then you rewrote it to use e-tuples, and then it was really slow.
Did you go straight from really slow?
Okay, so
yeah.
I mean, there's some point in making this faster, but on the other hand, you will not reach a speed, that's really acceptable for if you want to do really serious stuff.
Because the coefficients are generic anyways.
Yeah. So, so the reason why I stopped worrying about this implementation is because we have this implementation. And the whole idea is that Singular is really fast at basic arithmetic and pretty much lots of other stuff. And so the task was to link against Singular directly on C level to avoid the calling overhead, right? I mean, you don't have to use pexpect, so this is much faster. You can't do basic arithmetic using the pexpect interface. So this required us to convert Singular to a shared library. And actually, the Singular team was quite happy about it, and our patches are accepted upstream. And by now we're really good friends. So what it provides right now is only final fields, but including extension fields and Q. And as far as I know, this is the fastest implementation of multivariate polynomials over final fields, especially prime fields. And there's this kind of Feynman has this fast mult benchmark, and for this we are twice as fast as Magma. We're just doing this. So the basic arithmetic in Singular is just amazing. They're really fast. If you have a fast base with implementation, I will talk about Q in a second. There's lots of hidden treasures. I was talking about that earlier. There are lots of hidden treasures inside Singular. So if there's stuff Singular can do really well, just speak up so we can stuff that needs to be wrapped directly using C. I mean, computing in Gripner base usually doesn't make sense to go through the hassle and using C for this because it takes 30 minutes anyway.
Well, it depends how large the result is, but
okay, yeah, that's true.
not because pexpect is quadratic, so if you get a gigabyte as a result, it's going to suck.
Yeah.
So there's that polynomial you're multiplying that with P. So that has every monomial up to total degree 20, is that correct?
Yeah.
Okay. Just trying to get a sense of what it
Unless 32,003 is a multinomial coefficient, but I don't think it is. Yeah.
So is that, it's basically doing dense arithmetic then?
Yeah.
Okay. So
yeah, this is dense, but I mean the Singular stores basically lists of it's like in a sense these are arrays and these are lists, ordered lists. But internally, this is for basic arithmetic, but if you do, they have different representations for different purposes.
So does it decide heuristically this looks dense or this looks sparse and it uses a different algorithm?
No, it uses lists all the time, but if you do a Gripner basis calculation, you want to use something called geobuckets, which is like an
GeoBuckets.
GeoBuckets. Yeah,
but for a multiplication like the one you had up there before,
it will use the list implementation.
it uses what?
The lists.
So but is it using like an FFT algorithm for the actual multiplication?
I don't know, but I've never checked.
Okay.
It's,
I think multivariate polynomials could what they say FFT or
well, you
don't
can
think
do
so.
an FFT to do dense multivariate polynomial arithmetic, but if you start out with this like a sort of sparse-like representation, then you have to decide what if you're going to do it, sparse or dense. And
Maybe they do it. Maybe sometimes if they make a decision, maybe it's bad sometimes, but I never came across that situation. So.
But the usual representation of that arithmetic is usually sparse.
Yeah, except that example is really dense. So
Yeah,
that's-
well, but I mean, it's
yeah, I
like
mean,
a
it's
benchmark.
something in the order of what is it? Sort of 10,000 coefficients or something.
Well, but in any case, so Magma, so it's probably a safe bet to say they have a sparse representation only, and they are still their sparse representation is better for dense cases than Magma sparse representation for dense cases, because it's probably a safe bet that if you do multivariate stuff, you probably want to go for sparse.
I just tried that in Sage and Magma. It's twice as fast for me in Sage and twice as fast in Magma.
I mean, your
Almost.
computer is twice as fast.
No, it's exactly the same. Something funny.
Yeah.
Well, the times are, the ratio is the same. Maybe you timed it on battery or something. I don't know. It's very strange, actually.
Yeah, it is.
Something else running?
No, it's CPU time, so it shouldn't.
Yeah.
That's strange. Yeah, I get 0.14 and 0.29. So,
Superior operating system.
yeah.
Whatever the ratio is, it's fast, it's not, there's no complaining about the speed of the basic arithmetic of singular over finite fields. It's just stick to that. So, but if there's anything in singular you want, like I recently added matrices over polynomial rings. So this is stuff, you can do now directly using the C interface, which is, I think, cool.
Actually, I'll ask you that.
Okay. So, and this slide is supposed because there's kind of this rumor going on that singular is really, really complicated and you shouldn't touch that code, and if anything breaks, just run to Martin and
Is
fix
it? Where does the rumor come from? I think the build system.
A large part of it.
I think the build system scares people off because people are like, the build system's really terrifying, and then you think that all the code's going to be equally terrifying.
I mean, they use some dirty tricks, but overall, it's a quite large group that's working on singular. So there is, they're calling conventions and there are, API documentation and so on. So it's not as bad. And to show you that you can actually understand what's doing it, this is the act of the M polynomial underscore live singular, and all it basically does. So one of the concepts of singular is that you always have a global current ring. So basically what you do beforehand, you check if your current ring is the right one you want to use. And then, because these guys always destroy their input, so you copy them before, you get something out, and then this is the stuff you have to know, you have to call normalize afterwards, and then you're done. So, I mean, it's not, this...
What's CO?
Oh yeah, this is back from the old days when public CDEF functions from other modules weren't really callable, so I have this.
Have you ever got that to work? I still haven't been able to call public.
I thought it would be solved.
Yeah, it's supposed to be in the new version of in Python because of merging in LXML, but I don't know how to use it, and I've never got to.
Okay.
The naive way didn't work. I don't know. Have you?
No.
Okay.
So I ended up using this. The trick you
sure.
can use, you have an object and has a lot of CDEF methods. And so this basically just is a constructor for M polynomial singular elements, and you just pass it there. So I mean, this is really short code, and you can really understand it. So don't be scared, and you can actually touch it. So about Q, I told you earlier that I would be talking about Q a little. So first, this is should be MPFR, right? Our Q is implemented MPFR using MPFR. How do we implement Q in Sage?
When you mean Q, do you mean the rational numbers?
Yes.
GMP.
MPQ.
MPQ.
Yeah, it's the
Okay.
MPQ layer. I mean, MPFR is just real numbers.
For floating pointers.
Ah, okay.
Yeah.
Sorry about that. So in any case, if you multiply, apparently, so the lower part is a live singular and the upper part is MPQ. And if you multiply, apparently lab singular is much faster. But if you add, it's slower. I don't know where that comes from.
Could that be because they're doing, no, it's like MPQ, that's reduction. Yeah.
Okay, it's black magic. That's weird.
Maybe they have very slow GCD.
Yeah, but when you multiply them, then you
Why
have
is
that all the time
multiplying
together,
so
and you still
fast?
gotta do a GCD.
I have no idea.
Maybe they assume they
Wait, what the hell? How's that possible? Doesn't make any.
Multiplying it how many times as fast as it is?
Well, yeah, I mean,
10 times.
in most rings, it's true that multiplications,
That
like
doesn't make-
like in a field, if you represent everything just as a power.
So did they not reduce it? Or
No,
something?
I tried.
How the heck are they doing that? I mean,
you're right.
they've got to be using GCD.
Oh.
I mean, you're doing exactly the same.
Because of those
Yeah.
areas.
You're doing exactly the same arithmetic.
Yeah.
No,
It doesn't-
you're not right.
I'm not right.
I mean,
Essentially-
we tried.
no,
I
I
mean,
mean,
just
If you have A over B plus C
No, but
over
there-
D as compared to A over B times C over D.
No, he's multiplying P times Q which are two specific rational numbers.
Numbers
Then he's
cast into the
taking those,
polynomial ring.
then he's casting them into a polynomial ring and making those as constant polynomials,
Okay.
and then multiplying them. And it's suddenly, since they're both using GMP behind the scenes, it's a little weird that one is 10 times faster than the other.
So that means you can make the multiplication much faster by artificially piping it through a polynomial ring? I don't know what the overhead is of extracting
There is
constant coefficient.
there is something very, very dubious here.
It's weird.
That needs to be tested on somebody else's.
They've got to be delayed.
Everybody try this on your own machine.
What's the answer? 0 by any chance?
Check the answers as well.
Yeah.
Okay, so try it. I can't explain.
Met with disbelief.
They wrote their own rational numbers implementation.
Oh, they don't. Oh, they
It's
didn't
not
know.
MPQ. That's why I was asking about
Is
Sage implementation
Is there
earlier.
something just bad about the rational number implementation in Cycon?
Small.
I don't know.
That's just doing one example, right? It's 3 million bits or something.
Oh, I tried it with. I mean, in the same range, I tried several examples and was consistent.
Oops.
Okay, are you all done copying this
No.
and trying this? Okay, so I,
Not quite done. I put in too large of a value of n and that didn't work too well. How many zeros? 6. Yeah, I put 7. Not a good idea. Ran out of memory. This ran takes a while.
Oh.
So you don't like to use zz.random anymore because now it has some funny
What's the
distribution.
percent time?
oh, okay, I could have used that.
Well, this is uniform, which that isn't. Wow, that's really weird.
It's happening for you too?
No, I haven't got there.
God damn!
Really? That's fast.
And I mean, look at the output.
Well, what is the output?
Is the
Yeah.
output correct?
I mean, they agree. If you call equals, you know, it's the same.
Okay.
Well, no, but it should be the same because you didn't. Did you save the? You redefined the-
Yeah. I tried. No.
Did you try one where the GCD was not 1?
No.
Because
I only tried the random example.
Probably R1.
Yeah, it's almost certainly 1.
Yeah. That could be an explanation.
Oh, there might be 2 actually. Actually, isn't it like pi squared over 6 or something, or whatever that thing is, or the GCD is 1? Or
6 over pi squared.
6 over pi squared, yeah.
Okay, so.
Just run a pi squared times.
I wonder why their sun so slow.
Okay.
Yeah, moving on.
Next slide. There we go. Okay, the Commutative is now really GPL'd. And this is a library for doing commutative algebra. I don't want to talk too much about it because Mike is going to give a talk about it. And there's actually already a wrapper for this, and it was written in April 2007 by Michael and me within 5 hours. So it's really a straightforward library that's fun to work with. So getting started is much easier than getting started with Leipzig. Yes.
So actually return to the previous slide. What inspired you to test that?
Make sure
why?
that it wasn't
Because
slow.
there's the rumor going around that Singular's polynomial arithmetic is much faster than Magma's, but Magma's arithmetic over Q is much faster than Singular. So it evens out at some point.
How does that benchmark play out in Magma?
I don't know. Didn't try it.
I'll try that. Back to the
I
previous
was
slide.
listening to the rest of your talk.
Okay, I just let you play with it. That's my talk. Thank you.
We can hear the words.
Screw the rest of it.
So, Cocoa-Lib, focus people. Our patch never made it upstream because by the time we wrote this, we tried FP for this, and the basic arithmetic seemed slower than Singular, and we weren't really sure, why to push it forward right now. But eventually, it will end up to be in Sage, because over the reals and the complex number, it's probably a very good choice to use Cocoa-Lib because they have so much cooler algorithms for these space fields, if I'm not mistaken. You can correct me now.
Yeah,
It is. It actually had some discussions with the developers in Italy, and we're using the very general polynomial ring, not the cool and fast one that does all the stuff inline. And also, I did comparison for Buchberger over CFP against SlimGB, and also looked in detail at what degrees and so on they were in, and they pretty much would do the same. They would do this, take the same path reduction-wise, but they will be within 5% of each other. So the arithmetic, given, well, taking away the call overhead, should be pretty much the same as these for FP.
Okay.
But due to the internal structure, it's going to take some work on our side to actually eliminate the problem of the call overhead.
Okay.
Because it's the heap versus stack thing, and we have that ugly copy operator on the return, and it's just all, well, I'll talk about it Tuesday, I guess.
So in any case, this is hopefully going to be in stage in the near future, and it's going to provide some exciting functionality as well. And any questions should be directed to Michael. Another implementation we are currently working on is Polyboring. It's going to implement a Boolean polynomial ring. So as I said earlier, this is actually written down. This is a field ideal. And this is quite, this is a ring I'm very excited about because it's very relevant for what I do. And it's also supposed to be relevant for coding theory and stuff like that. Polyboring is conjectured to be very efficient. Our wrapper isn't quite there yet, so I can't really, if you take really large polynomials and multiply them, for instance, in Polyboring, it takes, basically no time. If you do the same in singular, it might take, several seconds or something. And the reason is that they are representing polynomials as zero-suppressed decision diagrams, so you can represent very large polynomials quite efficiently. Book and Aerocal is working on the integration right now, and we have a prototype available, but we cannot distribute it yet because actually Polyboring isn't released yet. But by the time it is released, we should have our wrapper ready, and so the day they release, we should be able to get it in stage. And I will show some. This is why I said conjectured. I didn't have the time to verify the benchmarks, so I will show some benchmarks from their paper, from the authors of Polyboring, which are Alexander Dreyer and Michael Brichtenstein, by the way. And Michael Brichtenstein is also in the singular team. So Polyboring will also be in singular. So after the technical details, so what can we do? So the first thing is that sometimes if you say, well, we can multiply polynomials, this isn't that fast, people will reply, well, who cares about polynomial multiplication? Because in the multivariate case, the only thing you care about is actually multiplying a monomial with a polynomial if it's, eventually everything is about Gribner basis calculations. But I claim this is not true. There are algorithms which are really interesting where you actually multiply real polynomials with real polynomials. So this is relevant, and it's good that we are fast there.
By the way, Magma, if you multiply the two rational numbers, the random ones, it takes almost exactly the same time as Sage. Actually, Sage is just slightly faster.
Okay.
But if you do it with multivariate polynomials, then Magma takes about twice as long as with rationals.
Okay.
So 7 seconds. So Magma doesn't have that bizarre speed up that Singular has. Maybe we should switch using Singular for a rational number arithmetic.
No, addition was so much.
Yeah, I'm just kidding. That's weird though.
So I'm just saying we need fast basic arithmetic over multivariate polynomial rings. We are fast there, which is really good. And we also have all the basic arithmetic in place, for instance, to prototype a Gribner basis algorithm or something like this. And this is, well, at least to me, this is one of the uses of a general purpose computer algebra system. Like, you just want to test, if the algorithm works, if it's more efficient, if it's, okay. You just want to play with, let's say, small examples, and eventually you will, implement it in C or something anyway. But this has to be fast and it has to be convenient. So, and to show that we actually can have all the, engine in place to write a Gribner-based algorithm, this is Buchberger's algorithm. It's a really simple algorithm. To understand what it does, please remember that a Gribner basis is that the set of the leading monomials of the ideal spanned by G, and G is the set of polynomials, is equivalent to the set of, if you take the leading monomials of G and you look at the ideal generated by those, these two sets are equal. So basically what we're trying to do is find an element in what that is in the ideal generated by G, and this is consequently in this set, which is not in the first set. Oh no, the second. So it's really, in a sense, quite straightforward algorithm. So this Buchberger's algorithm, this computes the Grübner basis for you, and so and this slide is only there to show you that you can write code which looks quite nice and which does what you want. But it was kind of nice, and you can write it down. It looks pretty cool. But let's look at some benchmarks. So this is you can actually call if you have an ideal. Katsura is a standard benchmarking ideal. And you have an ideal, you have this massive Grübner basis on it, and you can say, okay, use this algorithm. And there are these algorithms I just showed you are Buchberger 1 and Buchberger 2, and this Buchberger 2 is actually an improved version of this. It's more clever. And for Katsura 7, it takes like 260 seconds. And if you just do the same using Singularly, 0.46 seconds.
It's not using the pxspec stuff at all there?
No, no.
So you can actually call the, like SimGB is in C++?
Yes.
So with the library, you can call anything if it's in C++ and nothing if it's in interpreted code? Is that how it works?
Yes, I have some
like
preliminary version working where I can actually call interpreted code from Singular.
Wow.
But that interpreter doesn't terminate, so it's the last thing you call. But this is fixable.
Yeah.
I mean, it's just one email to Hannes and say how do I do this, and he will reply, and then it's done.
Yeah.
So eventually we can even do this.
Cool.
But it still is going to be slow because it has to be interpreted first. But it should be faster than pxspec anyway.
Mm-hmm.
You default to Deckard links?
Yes, yes. All polynomial rings default to Deckard flex. And just to show you why, this looks kind of, oh wow, this is so much faster. Let's compare it against Magma. And this is already a show off, so we can, use Magma behind the scenes, which is kind of nice if we want to compute. So how long does this stuff take? And we just, go to Katsura 8, which is an 8 variable Katsura, and we take like 6 seconds for with Singular, and we take like 1.5 seconds with Magma. So the rule of thumb is that Magma is really, really good at computing Grübner basis.
Is Magma using pxspec here?
Yes.
Yeah.
Yes.
So probably the time that counts is the 0.5, like you said.
I mean,
the wall.
Oh yeah, the CPU.
It probably takes half a second to start up.
CPU.
Yeah, look at this. The CPU time. this stage
moving stuff back and forth.
takes more than half of the actual time.
That's moving stuff back and forth.
Yeah.
Yeah. So yeah, actually it's much faster. For this example, like probably 10 times as fast as. So
Yeah.
they have some quite efficient. I mean, it's not in every case because there is no such thing as a fastest Grübner basis algorithm because you can always produce benchmarks where your algorithm comes out on top.
Even with Toy Butchburger?
Interesting. No. Okay, there are particularly bad Grübner basis implementations.
Okay.
It's the inhomogeneous case, which is interesting. There's like 3 different strategies to do it.
No one knows.
And the recommended way, you cannot determine, there's no heuristic to determine which one is the optimal.
There's only 3?
Yes.
3 core?
Yes. So what you do is you run 3 cores.
If you have enough
that's the
RAM,
recommended way. You run
Yeah.
all 3 computations, and once the first one finishes, you kill the other 2.
Yeah.
That's not even a joke.
Well, but you have I/O problems.
You can do
When somebody had the internet rock, paper, scissors competition, this was the program that won. It forked 3 processes and she was the one that won.
What happened when you played it against itself?
Whichever one goes last
Serious
wins.
race.
Okay, so these are the benchmarks I was talking about earlier. I took from the slides of Michael Brickenstein, and these are all cryptographic examples. So these are kind of examples I care about, and I don't care which is the fastest algorithm. I care about the algorithm that solves these problems the fastest. And as you can see, there's this AES is probably most well known to you, so let's try this guy. So it takes 3.2 seconds in Polyboring, it takes like 20 seconds in Singular, and it takes, they claim it takes 400 seconds in Magma. And the reason why Magma is slower here is that they are actually computing with lexicographical term ordering, and Magma's strategy is particularly bad for that situation. So this doesn't really represent Magma. But so this is why I'm saying it's conjecture to be fast. These are the only benchmarks I have so far.
Is that the improved SlimGB and from Polyboring, or is it singular SlimGB?
This is Polyboring and this is singular.
The singular, that's SlimGB, right?
Yeah.
Yeah, because
Because they're
Singular beats Magma everywhere here too, except the bottom one.
Yeah, yeah. And so, but they state that this is a very bad benchmark for Magma. So it's not they are trying to hide it. I'm just saying, don't take these numbers too seriously.
Now the question is that, because from my understanding is that Polyboring contains a different version of SlimGB, an improved one that did not flow back into the official singular tree.
Yeah, they have this new criterion, which is a bit better, yes. That might also contribute to that fact.
Okay.
Also, why they are doing lex here is because in cryptography you usually want to compute with lexicographic term ordering because you want to solve the system. You're not interested in all the rich algebraic structure, you just want to have one solution. And this is giving you, lexicographic term ordering is the right one to do. On the other hand, your system is supposed to have one solution anyway. So just computing reduced decreflex Grosvenor basis is usually as good.
Now, what kind of cryptographic application is this?
It's crypt analysis. So you basically take your cipher, you express it as a quadratic equation system, you try to solve it. And yes, we don't know if this is any good. But it's interesting, it's fun.
It's really surprising because Poggi broke the HFE challenge too, which nobody really expected.
Mm.
Yeah, but this is because HFE has a hidden structure.
Yeah, but I mean.
So there's a lot of research going in this direction, solving sparse, overly defined quadratic equation systems over F2 and doing this fast. So this is kind of, it's cool stuff. Anyway, we can do other stuff. One thing we can do, and I'm not even sure, I think Magma cannot do this, computing local orderings. I might be wrong here. So stuff like the negative decreflex ordering, it's basically just you reverse the ordering. So if in decreflex x is smaller than y, then it's the other way around in negative decreflex. And in this example, we are trying to compute the multiplicity of the origin as a root. And apparently it has multiplicity 80. And so we can do this in Sage, and this is also because of singular. And I think this is, for some people, really exciting.
Is that one of the sort of things that Singular started out trying to be good at? Or
could be, yeah.
Like working, I think it was working locally.
Yeah. This is their home base.
Mm-hmm.
I think so.
Cool.
Another thing that's quite cool, which is not as flexible in Magma as it is right now in Sage, and this is, again, when I say Sage, I mean Singular, because they implemented all that stuff, and all I had to do was write some nice function to call their function. So you can have block or product orderings. So basically anything in the first block will be greater than anything in the second block, and inside your blocks you can have any term ordering as you want. And you can even have local orderings in the second block and global orderings in the first block and all this kind of fancy stuff. And this comes in handy if you, for instance, in the cryptographic examples, I was, it's quite natural if you have a block cipher which repeatedly does the same thing, divide that into blocks and work with that. So that's kind of cool. And you can look at it and you say, okay, the first block is lexicographic term ordering with 3 variables, and then you have the second block and so on. Also something quite handy. Okay, we can do a bunch of higher-level operations on ideals, like complete primary decomposition, can get the syzygy module and elimination ideals and stuff like that. So if there's anything missing, just let me know, it's easy to add. Also, I'm just running through, cool stuff you can do, and it's because it's state of the project. Another thing is like there's this project called Symbolic Data, and it's supposed to be the go-to place for benchmark ideals and test ideals. So, so we have a wrapper for that one. So if you install that database, you can get access to these 350 ideal bases, and then you can start, throwing your Grübner-based algorithms in there and so on, which is kind of nice. This is the last slide about what can we do. Just recently we added something for MQ. MQ is the problem of solving a multivariate quadratic equation system. So again, this is this cryptographic application. And we have a generator now for AES equation systems in Sage. So anybody can now, because usually it's kind of annoying because all these cryptographers, they invent their own crappy toy ciphers and then they break it, and you don't know, is it really good, their attack, or is it just their toy cipher? And also it's a bit tricky to implement this equation system generator because the key schedule of AES is well complicated. And so so we have it in Sage now, so everybody can just spit out AES equations and boost around. I can solve this fast. And at the bottom here, you see if you happen to know a technique to solve this polynomial system, then you basically destroyed AES. I mean, so I know how to solve it. I mean, fast. So if you can do this, it has 8,500 polynomials in 4,200 variables, so it's overdefined. It's sparse, and most of these are even linear. So it should be easy. Go for it. And eventually there will be, a bunch of more ciphers like HFE, Michael mentioned earlier, and stuff like that. So those really, and you can do like, give me the coefficient matrix of that system and do some fancy stuff with it. Okay, so this is this last slide. What we can do? It's about what we cannot do. One thing that has been requested a million times is that we need at least decent basic arithmetic for multivariate polynomials over rings. So there is, and also computing Grübner bases over these rings. And there is an unofficial preliminary version of Singular that does it. So there's hope. They are working on this. Also Commutative, it's on the to-do list, but it's not there yet. And Macaulay 2 can actually do this. But Macaulay 2 is kind of hard to build, and it's only an optional Sage package for now. But once you install Macaulay 2 and you say, give me the Grübner basis over for this ideal over Z, it actually computes over Z and not over the rationals or something. And also, we obviously want more base fields for fast arithmetic. And these are just the stuff we can easily add, like number fields, because Singular supports them, and the reals and the complex numbers. Okay, anything else we should really have, we can come up with right now?
So can I ask you a question about this slide? So as somebody who would really like Zmod n, I mean, what are the prospects for seeing that anytime soon in either Singular or?
But there is a version. I have a version of Singular that does this, but it's not released yet.
That does what? That does just the arithmetic, or actually does proper Grübner?
I think it should even support Grübner-based calculations. So there's one Singular developer, Oliver Wieland. He's working on that, and he said he's almost there, but it's not in the official release of Singular yet. So there must be some issues. But I mean, eventually it will be there. And also, one guy in the Cocoa project is working on this, right?
Well, the thing is, the Grübner base, I think, just What do you mean, like the Z and Zn as coefficient rings for multivariate polynomials, or what?
And group-based calculations.
Yeah, for the arithmetic, it should work.
Okay.
I'm fairly certain for the, I've lobbied to get it to get the Gripper basis for rings in, but or at least for ZZ, and it was promised to me, but actually, as it turned out, it was then postponed again, and I need somebody who complains actively that it gets done. Well,
Yes.
Okay, Michael will hand you the email address of the Cocoa team, and you write them daily. You know.
Massimo Caboara. Just call him Carbonara to piss him off.
That's a good way to ingratiate yourself.
I call him that every time. Carbonara. His name is Caboara, and it's a very odd one for Italian names. But if you read it, you always assume
What's the time?
It's like 10 to 8.
So you're like,
I just should leave that up then. I mean,
But we all want to see it so badly.
I'm
Is it
so
really?
over time.
Are people still willing to listen to me talk afterwards?
no.
It's optional, isn't it?
Yeah, sure.
Sure.
Okay.
Yeah.
So this has nothing to do. Well, it has something to do because I care about it, but it has not, direct connection to commutative algebra. But the simple question, the simple thing you would want to do with a sparse matrix over finite fields will give you the reduced row echelon form. And apparently, it's really hard to find any implementation of it. You would think, well, Magma can do it, but apparently they can't. You cannot ask Magma for reduced row echelon form of a sparse matrix. And you want to work around it. You can even, if you ask it for the null space, you get a dense null space. So basically, all the stuff in Magma is dense, and you can't really. And this is quite surprising. Linbox, you would say, okay, Linbox, they're quite famous for their sparse linear algebra, and they actually almost do it, but in preserved memory, they kill the rows they are done. So like you're in the lower part of the matrix, and all the upper part will be cleared, because they don't care about the row echelon form; they only care about the rank. And there's also, usually when I say I want to reduce row echelon form, I mean without column swaps, for my application at least. And eventually it would be really great to have such a thing that doesn't involve row swaps.
What are you talking about?
No row swaps?
I just don't even know what you're talking about. What do you mean, no row swaps?
Like you say, oh, this row it's a pivot row, and then I swap it, put it on the top.
How can you put it?
Sorry.
How can you put a matrix in row echelon form if you don't do row swaps? I don't understand.
Probably, but okay. So here's the thing.
You want to know which rows ended up where, right?
Oh,
At least that, yes.
okay.
So maybe if you
I see.
maintain a
So you want information about the
array, that should be
transformation.
good. But I don't know if F5, this is the algorithm I'm talking about.
Yeah, okay.
And I don't know if F5 says, okay, if you can't do it any further, we just stop,
Mm-hmm.
or if it's good with the permutation array. I have to check.
Okay.
But probably, yeah, the permutation array is the way to go.
Okay, so what are you allowed to do if you're not allowed to swap? Like, add a,
Adding and scaling.
you can do a swap with those two.
It should be, right?
Because
If it doesn't IML.
you add a row to this one and then subtract the sum from the top.
Yeah, I mean, it's just like the standard XOR to swap X.
Okay.
I think IML does an in-place incremental row echelon form where you then have a permutation index, so you can determine which row ends up where.
Okay.
But that doesn't make sense, because if you're adding the rows, you can do a swap without even noticing it. You can add multiple.
Yeah, but you're talking about F4 or F5?
F5 right now.
F5? Yeah, I thought because you can't really do a traditional row echelon form, but we can do that later.
Okay, yeah, but this is not too relevant right now, and I'm so over time. Anyway, Linbox, just doesn't give you the reduced row echelon form. Sage has a native implementation which is surprisingly good, because so far as our benchmarks go, it's surprisingly good. I mean, you would expect, it's just, I don't know, William, how long did it take you to write this?
I don't remember. Not that long.
Benchmarking depth of coding?
Sorry? No.
Probably a week.
No, when we benchmarked it, it turned out to be quite efficient.
I think it was a week.
Okay.
Yeah. Because it's just a straightforward algorithm with one drip of intelligence.
Yes, and this is quoted there. We use Gauss elimination in a slightly intelligent way, and that we clear each room using a row with a minimum number of non-zero entries. And this is the only strategy that's involved there.
It's painful though.
Actually quite good. And the stuff we benchmarked again, actually Walter Weinmann benchmarked again, he's working on some code by John Cremona, his GOM package. So Ralph is gently ripping out the linear algebra. And for really sparse matrices, this is way faster than what we have in Sage.
Oh yeah.
So, and this is supposed to be quite fast, and I just learned this noon about apparently there are other implementations.
Any news about that?
No, we didn't look into that.
Okay.
So this is the slide where you should be seeing benchmarks for GON, but
They're gone.
They're gone.
Okay, if you still have time, there's this this kind of idea how to do, because the main issue with computing the row echelon form of a sparse matrix is the fill up, that you end up, in between you end up with a, even if it has a full rank, in between you end up with a dense matrix. And you don't want that to happen. So this is the, William wrote this, came up with this idea to have a rational echelon form via the solver. And this is like the adaptation of this idea to the sparse case. Because in this situation, we never actually write down the intermediate steps. And the idea is that we can actually compute the rank and the pivot columns without actually computing the row echelon form, because we just use these symbolic reordering, which is column swaps and clearing the upper part of the matrix. So this should give you some memory preservation, and it should be faster. And I think I even have some complexity estimations that mean nothing to me. Yeah, I have them. But in any case, so you can do it faster. This is basically the assumption this operates on. So what you do, you basically find the rank of the matrix, and you find the submatrix, a square submatrix of full rank, and then you solve. And then eventually you have some rest, which is not in that submatrix, and then you solve. So it's quite a straightforward idea. One of the problems is that we don't have a matrix-matrix solver, so we have to repeatedly solve for vectors. But as you can see, so what are we doing? Well, we're computing the rank twice. So this is, if you do it naively, so we have 2 Gaussian eliminations. And then you solve at the end, so this means 1 inversion. So if you just do it naively, you end up with 3 times Gaussian elimination. But as the first 2 are supposed to be, more than a factor of 3 faster than Gaussian elimination, you're getting a gain, and the Wiedemann solver is supposed to be much faster also than just inversion. Okay, this is the Sage code to do this, and it's this Sage code pretends that you can compute the pivot columns without doing the row echelon form, and this would require a patch to Lindbox. And right now, so write to a Lindbox mailing list and say, yeah, we really want the pivot columns out, because they computed them anyway, they just don't return them. And so here are some complexity estimations that are meaningless. In any way, I would claim this. If you have a rank, if you have like a rank which is like half a dimension or something, that's probably won't give you any benefit. But if the rank is bounded away from like if the rank is almost n, or the rank is far away, it's very little. Then you have a submatrix like 10 times 10, and then you can invert it. Or you have 1,000 times 1,000 dense matrix, and you can invert it and then solve. So if the rank is really bounded away from the middle, then it should give you an advantage. Yeah. If anybody has any ideas how to improve this, just let me know, and thank you. Questions?
showing that rational business again. So the multivariate rings. And the first suspicious thing is that the time it takes to multiply two fractions like that is exactly the same time that GMP takes to multiply the numerators and multiply the denominators. So, and it's difficult to tell if it's actually reducing anything, because when you pull it out back into Sage to compare it, then Sage sits there for a while, it thinks about it while it's converting it, right? So I think it's doing the GCD there.
What about when you print it?
Well, when you print it, I've tried that, but it's hard because like
string wrap, or
they're enormous. If you actually want one.
But you can compare strings, right?
Every once in a while, GP
yeah,
will give me a rational function in the form -1 over -x, or even
Yes.
more than that.
Yes, I think that's been fixed now in GP.
It's not fixed in M polynomial Sage.
Yeah, but that just might be the solution later. Maybe I'm even supposed to call something to normalize it afterwards and just forgotten, that's why it's so fast.
No, I'm saying that I don't think it's doing a GCD. I think internally it's storing that fraction as just one enormous numerator over one enormous denominator, which might even be 1.
And then it does the GCD later.
I don't know. And, it might be doing it when you pull it back out to Sage, because then Sage has to create a Sage rational object. And it throws in the numerator and throws in the denominator, and GMP says, wait a second, while I reduce that for you.
oh, that makes sense.
And it has time to say that too. It takes a while.
Okay.
So we do lazy printing.
Well, probably if you just convert to a string, it should.
Yeah, but that's going to take a long time. Anyways, right? Unless you can ask it to do a string in base 16 or something.
No, no.
Yeah.
So let me ask, number one, who wants to stay here another talk?